Imagine a skyscraper flying at Mach 25, a massive structure tearing through the atmosphere at 17,000 miles per hour operates on the edge of reality. When prototypes of these massive vehicles explode, it looks like a catastrophic failure. Critics point to the fireballs as proof the design is flawed. But the traditional aerospace model is flawed. The industry standard was the equivalent of flying a 747 from New York to London, parachuting out at your destination, and letting the aircraft crash into the ocean. You throw the plane away after a single use. To build reusable spacecraft, engineers use a testing framework called exploring the corners of the box. This involves deliberately subjecting hardware to the absolute worst-case scenarios, the extreme edges of the flight envelope, to map exactly where physical limits lie. The explosions are intentional. You have to push the hardware until it shatters, because finding the exact point of destruction is how you guarantee a vehicle survives when it actually carries people or cargo. We can see this framework in action during a recent Starship test flight. Engineers deliberately removed protective heat shield tiles from some of the most vulnerable locations on the hull prior to launch. Then they brought the ship back into the atmosphere on an unusually steep, extra-hot trajectory. They engineered a situation to guarantee the vehicle would face maximum aerodynamic and thermal stress right where it was completely unprotected. The plasma burned actual holes through the steel structure. Yet, because the underlying design had been tested so aggressively in the past, the vehicle remained robust enough to make it through the atmosphere and execute a soft landing in the ocean. This cycle of intentional punishment forces engineers to brutally simplify their designs. You can trace this directly to the Raptor 3 engines powering these rockets. They lack the maze of external plumbing found on earlier versions, resulting in a clean, tightly integrated power plant. Despite being smaller than a conventional jet engine, a single Raptor 3 produces twice the thrust of all 4 engines on a Boeing 747 combined. Forcing components to survive extreme failure states eliminates unnecessary weight and complication. Stripping away the excess yields machines capable of producing immense power. Imposing extreme physical constraints also dictates terrestrial manufacturing. When tasked with making the Cybertruck bulletproof, that single requirement drove every subsequent design choice. To stop a 9mm bullet, the exterior requires ultra-hard, cold-rolled stainless steel. That material choice immediately breaks traditional automotive manufacturing. If you put ultra-hard stainless steel into a standard stamping press to curve a door panel, the steel doesn't yield, it destroys the press. Since you cannot stamp it, you have to fold it. The assembly machines bend flat sheets of steel far past the desired angle, allowing the metal to spring back and settle into the correct position. The brutalist aesthetic of the vehicle is the direct mathematical output of solving the physics problem of bending an unyielding material. These extreme engineering constraints stem from one reality: Earth's exceptionally deep gravity well. Gravity is set to maximum difficulty here. If the pull were even 20% stronger, conventional rockets couldn't generate enough thrust to escape. We'd be permanently stuck. The only technological mechanism powerful enough to bypass that planetary constraint is full and rapid rocket reusability. Reusability flips the economics of spaceflight entirely. Landing and flying the same vehicle again drops the financial cost of reaching orbit by a factor of over 100. Driving hardware past the edge of destruction and scrapping traditional manufacturing rules is the math required to close that economic gap. It is the physical equation that allows humans to establish a civilization on more than one planet.